stuff. Like we'll go from the content compression to classical communication. Like we done, like we saw, like entropy. Like we need, like for compressed, to have a rate of compression superior to entropy, etc. And that it can be cool. But now we identify classical communication. So basically, what we want to point in here is that in classical communication, the naive approach will do, like to do measurements, like product measurements. So suppose you have a message that you encode, like two different channels. Like let's say your message is M, and so you have like x1 of M, x2 of M, etc. And so I don't know, xn of M. So that's your encoding of your message, and so you have epsilon1, have epsilon 2, which is your encoding channels. You have ADs stuff. After you go through the channel, and after you do like decoding stuff, D1, D2, and DN, like do codec 3. Like let's say here we know we have like three stuff. Like we have our message, I don't know, like we have our message like AABBCC. And so yeah, here we encode AA, here we encode BB, and here we encode CC. But yeah, so we have our encoding and this three. So that's just normal stuff, and after you do POVM, and so you have the results for measurements to recover AABBCC. You recover AABBCC at the end. And so that is like many independent uses of the channel. So here, that's separation between Alice and Bob, and here is Bob in a way. So there is no use of quantum mechanical effects like in the classical case, like Alice and Bob agree on the codebook with classical code words xn of m, which is here, corresponding to a message aimed to transmit. So LA generates quantum codebook with quantum code words. So here, like why here we can say like it's like row x1 of m, here's row x2 of m, and here's like row xn of m. And so at the end, like the formula will be like row xn of m is just x row x4 of n of m. It's just like the tensor product of then like row x1 of m, so row x2 of m, row xn of m. So yeah, Bob performs individual measurement at the outputs here, like here, like for each D1, D2, D3, by exploiting a POVM. And so it's just like Born rule, which say like we have like the POVM for measurements multiplied by the states itself, rho xe of m. And so because you are doing it multiple times, we just take the trace of it to have the identity, and it's just equal to like if we do it for each step, it's like the product of one to this to the trace of this, that's like product measurement. And after we have our channels that apply on a state row xi of m. And so that's it. So yeah, it's equivalent to the NID identically distributed independent instances of classical channel, which is Born rule. So what we can see is like from Shannon classical theorem, the optimal rate of communication, like the accessible information of the channel. It just we just call it the accuracy of it, you know. Like we have the accessible information of the channel, but here there's no use of collective measurement of entanglements. Like if we let's call like this, that will be useful for just after. So just the maximum information that you can have access to the channel. Like here we just represent it without collective measurement of entanglement. But now if we consider coding for the tensor product channel and their n, so suppose here like when you encode, like you take two photons, for example, and so you have A and N. So you encode two photons, so you can have this way, this time some entanglements on here too, AI and N, and so here, boom, of B, and same here, like then you can say have entanglement, and we can have new properties, and that the rate of classical communication that the one we had before, you know, the diagrams before this n that without those two liaisons with two photons, like when you only have one photons, you have the information is like less bigger, you know. So in our case, like it's like we have two, and the rate is like 1 AA of AC of n XOR n, which is superior to AAC of NN of n. You know here two photons. Suppose you have three, for example, we put a third n channels, then it will be even bigger, etc. So you add information. Yeah, because you know this is a special case of this. After n XOR n, like n XOR n will be a special case because it's just n XOR I, and yeah, so this suggests that the ultimate classical capacity of the channel is the regularization 1 over k of AIC of n XOR k, and just I regulation of n, which is equal to this. And so with the limit of this like being of k being to infinity, and yeah, that's how we can think about it. But like in reality, it's like hard in reality to know about it. Like when we have like a lot of n stuff, you know, like infinity stuff with infinity photons, for example, to see all the link of entanglement. Like it's really hard to know to what it is equal. It's intractable in general because as information AC is not like additive in general. And so the idea is like how can we what we want to know is like how can we bound it, how can we bound this regularization of like limits of k being of over infinity of 1 over k of IIC of n XOR k. And so the answer is just we need the Olivo bound that we will see in the next video. Where you must remember that I see just the information, like the accessible information that relies on optimizing, like we can have by optimizing what we have control over, like the choice of probability p of x, as the choice of the quantum state, and the choice of the measurements, the p of m. So yeah, that's it. That's just the maximum of the mutual information between two variables, optimizing between on three stuff, which is the probability of the message, the quantum state, and POVM. But yeah, we'll see how we can bound this regularization thanks to the level bound in the next video. Okay, thanks everyone.